So I talked to a few of you as you came in, but I would like to get a little feel for the audience here. Is there anybody here who actually works with Kotlin day to day? Yeah, a few of you. Anybody who regularly works with Java? And what about C#? No. JavaScript? Ruby or Python? Anybody here like professional wrestling? No, okay. Well, I used to be into professional wrestling when I was a kid, back in like 4th grade. And this was back in the days of like Hogan and Andre and Macho Man, all those guys. And the one-on-one matches were always a lot of fun, but my favorite was always the tag team. And so if you don't know, tag team wrestling is when you've got usually 2 teams of 2 wrestlers each, and you've got one wrestler on that team who's in the ring at a time, and the other one stays on the outside of the ring. And a lot of times what would happen is, like in order to switch places, you'd reach out and tag your teammate. And a lot of times what would happen is right at the most critical moment, the guy is down on the floor getting beat down, he's about to get pinned, and the last moment he reaches out and tags his teammate, and the teammate comes rushing in, and the fresh gust of energy and saving the day. And so what I wanted to do is start off by introducing you to a couple of professional wrestlers. So on this side of the ring, we've got the Sledgehammer team featuring Sledge, and you'll never guess the name of his teammate, Hammer. On the other side of the ring, we've got the V team with Vandal and his teammate, Villain. Villain he's off screen somewhere. I'm sorry, guys. I was too lazy to draw a 4th wrestler, and he's not very relevant to the story anyway today, so he's out there somewhere. So let's see how this match plays out. So we start off with Sledge and Vandal in the ring, and Sledge does a suplex. Then he tags Hammer, and they switch places. And Hammer does a clothesline move, and then he tags Sledge, and they switch places again. And then Sledge puts Vandal into a figure 4 leg lock, and then he tags Hammer again, and they switch places. Hammer uses a pile driver on Vandal, and then he finally tags Sledge one more time, and Sledge steps into the ring and pins down Vandal for 3 seconds, and they win the match. Okay, let's write some Kotlin code. If we were to write this wrestling match in the most basic Kotlin, this is roughly what it would look like. We've got our main function here, and these print line statements are just, as you can guess, they just print out to the screen. So the main function is the entry point. Print lines are just sending out to the console. Now this works fine for a simple scenario where we've got just a bunch of statements that we want to print out. But in our real world code, a lot of times it's advantageous for us to keep related code together. So instead of intermingling the lines of Sledge and Hammer, I'm getting mixed up on it already. Let's separate it out so that we've got just the code for Sledge together and just the code for Hammer together. Now, of course, the problem is when we do this, obviously, it's going to change the order of the output, right? And so you can see on the far side there that all of the lines for Sledge are written first, and then the lines for Hammer are written second. And in fact, we've even got the pinning right in the middle, which is not supposed to happen. Pinning's supposed to happen at the very end. So the challenge is, how can we keep the related code together but still get the output in the order that we want it to be? And this is where coroutines come into play. So if we can take all of the code for Sledge and put it in one coroutine, and then take all of the code for Hammer and put it in another coroutine, then the coroutines will allow us to yield after each statement to go to the other coroutine, and the execution will bounce back and forth between those 2 coroutines. And that is the essence of what a coroutine is the ability for that execution path to bounce back and forth between those 2 different tasks. And when we've got execution that runs this way, where we're bouncing back and forth between 2 tasks, we say that it's running concurrently. With concurrent code, each coroutine gets a little bit of time to run, and then it can choose to suspend. It will yield its time slice to another coroutine, at which point that coroutine can step in, and then it can decide to yield as well. So let's update our code that we had before so that it uses coroutines. Now, in Kotlin, when you want to create and begin executing a coroutine, we do this with a special kind of a function called a coroutine builder. And there are a few coroutine builders that the Kotlin coroutines library gives us, but we're going to start with one called run blocking. And we're just going to wrap the entire function here with run blocking. Now, in case you're not as familiar with the syntax for Kotlin, I would like to point out that this is a function call. So run blocking is the name of the function. And then you see the code highlighted here is it's a lambda that is getting passed to that function. So even though it's not inside your normal parentheses, it's still an argument to that function. Make sense? Okay. So run blocking, as I said, is a function that creates a coroutine. It's called a coroutine builder. And then the lambda that we've got highlighted here is also a special kind of a function, a special kind of lambda called a suspending lambda, or a suspending function. And the superpower that this suspending lambda has is the ability to suspend the coroutine that's running it. So it's much like a tag team wrestler who can tap out and give the ring to somebody else. That's what you can do with a suspending function. It can tag out that coroutine that's running it. So when we look at this code, we can point to the coroutine builder. We see run blocking. We can point to the lambda. But which part is the coroutine? That's a question that a lot of people ask. And the coroutine is actually the instance of code that's created when we call run blocking with this lambda. So in other words, it's an actual instance of code along with configuration information and other data about its state, like whether it's running, whether it's paused, whether it's completed, any other state that's in scope for that coroutine. And this definition might sound a little amorphous at first. It feels a little hard to grasp, but you're actually already familiar with this idea at a different level. So let's say that you were to open up two different console windows, and in each console window, you were to run a command line application that simply counts from 1 to 1 million. You start both of those applications, and they're both going to be at a different point counting at the same time, right? They each have their own, each execution has its own instance. They're running the same code, but they're at different places, and one of them is going to complete before the other one. So it's the same idea for coroutines. It's an instance of running of code that might be running or might be suspended or might be completed. But instead of having this managed by the operating system, it's the same idea, just managed in your Kotlin application. So looking back at the code that we had before, we saw that the output wasn't what we wanted it to be. All of Sledge's moves are at the top, and all of Hammer's moves are at the bottom. So they're not trading places with each other. And so if we want our wrestlers to trade places with each other, we want to have each of the wrestlers in his own coroutine. So let's group the wrestling moves into two additional coroutines. We'll have one for Sledge and one for Hammer. And so far, we've only been using the run blocking coroutine builder that you see here, but we're going to use a different one. Run blocking is typically only used at the entry point for your application at the kind of the highest level as just a way of bridging from your regular Kotlin code to the world of coroutines. So instead, we're going to use a coroutine builder called launch. And this is what that looks like. Now, we're still getting the same output here, but we at least have them in their own coroutines now, and we're almost there. The last thing that we need to do is we need to get this into a place where the wrestlers can tag out. And so in order to get Kotlin code to tag out, we just need to suspend the coroutine. One way to do that is to call a function named yield. And you can think of this as the wrestler is just yielding the wrestling ring back to his teammate. And technically, it's actually the code is yielding the thread that it's running on, but easier to think of it that way. So here we've got a call to yield after each wrestling move. And when we run this, we finally see that we get the output that we wanted. Awesome. OK, let's review the different pieces real quickly. First, each wrestler's code is in its own coroutine. So we've got these two coroutines here. And then the call to yield is what it is that taps out that coroutine so that another coroutine can step in. And for what it's worth, we also have the third coroutine, which is the one created by run blocking on the outside there. And this is actually something we're going to come back to in a little bit before the end of the presentation, because we have one coroutine creating two more coroutines. And this puts them into a hierarchy of coroutines where they have a relationship between each other. And this actually is very helpful when it comes to things like cancellation and exception handling. So we'll see that later in the presentation. So as we've seen, the key characteristic of a coroutine is its ability to suspend its execution at some point and then to come back and resume it at some point in the future. That is something that a coroutine can do that regular code cannot do. Since only a coroutine can be suspended, it also doesn't make sense for us to call a suspending function when there's no coroutine to suspend. So in other words, if we were to try to call yield directly from our main function, we would get an error. Since we haven't used in this code on the left, we haven't wrapped it in a coroutine builder, there's no coroutine running it, and so therefore there's no coroutine to suspend. Doesn't make sense to do that, and that's why you get the error there. But instead, on the right, you can see the yield there is inside the launch and inside the run blocking, so there is a coroutine running it. Makes perfect sense. Now, what about those times when we want to extract a function? For example, maybe every time a wrestler tags out, we don't just want to yield the ring, but we also want to print a line to the console. Well, our usual idea would be to just create a new function and move the yield call inside of it. For example, here I've got the new function named tagout, and we're printing a line there and then yielding. But as you can see, that didn't work. And that's because this function tagout could be called from the right place, like we're doing here on the left, where it's inside of a coroutine, but it could also just be simply called from your main function, right? There's nothing preventing us from calling it from the main function as it is. And for that reason, and of course, in that case, there's no coroutine to suspend, so that's why we don't allow that. So any function that calls a suspending function also needs to itself be a suspending function. And we can do that very easily. We just add the suspend keyword to the beginning of tagout, and now it's a suspending function, and we can use it inside our run blocking and launch, and we will not be able to use it inside just the top level of main. All right, and now everything compiles fine, and we get the output that we wanted. So now that we've got the basics of coroutines figured out, let's see a few practical ways that we can use them to make our code run faster. It is time to meet Rusty Mechanic. He spends most of his days engineering and managing Bot1, his heavy-duty robot who works on construction projects. So one day, Rusty and Bot1 received a work order for constructing a new building, and their checklist for this project included 3 tasks. First, they got to lay the bricks, then they have to install the windows, and finally, they have to install the doors. Well, Rusty and Bot1 have a large pile of bricks on hand, but the windows and doors are ordered specifically for each project, so they have to be delivered from warehouses. Well, they arrived at the construction site ready to get started, and here's how the day went. Bot1 called the warehouse to order the windows that he needed. The delivery took a long time to arrive, so while he was waiting, he just sat on the curb and twiddling his thumbs. And once the truck finally showed up, he got the windows off the truck. Next, he called a different warehouse to get the doors. Same story there, sat on the curb, just waiting for that truck to show up. Finally, he laid the bricks, and finally he installed the windows, and then he got to the doors. And once the project was complete, Rusty decided that that project took way too long to complete. So this is what it looks like when we do just one thing after another, and we just have to wait. So if we're waiting on that delivery, we're not making use of our time doing anything else. And he had to do that twice, once for the windows and once for the doors. And then really the work that he was best suited to is laying the bricks, installing the windows, and installing the doors. And he didn't get to that until all the deliveries happened. So let's write some Kotlin code to model this project and see what it would look like. All right, this looks like a big splotch of code up on the screen, but it's actually very simple. There's no coroutines involved here. This is just, we've got 2 products. We've got one for the windows, one for the doors. And then we've got 2 functions, one for ordering a product and one for performing some work. And both of these functions basically have the same form, as you can see. We're just printing out that something is starting. We do a thread.sleep, which causes that thread to just take a nap for however long you tell it. And then we're logging out that the job was completed. And the only other difference is the order will actually return the item when it's done. And then with that, we can have a main function that looks exactly like what we just heard from the story, where we order the windows, order the doors, lay the bricks and then install the windows and doors. And when we run this code, it takes a full 5 seconds to complete. And we're going to see by the end of the presentation how we can speed this up. After watching a professional wrestling event on television, Rusty wondered about how he could make his construction projects more efficient. He thought, what if we could make our tasks more like tag team wrestlers, where they can tag out and let bot 1 work on one thing, then step out to work on something else for a while. So the next day, he decided to test it out. And here's how the project went. First, he called the warehouse to order the windows. Then, without waiting for them, he made a call to the other warehouse to order the doors. Then, without waiting on anything else, he got working on the bricks right away. And the doors were delivered while he was laying the bricks, and the windows were delivered just shortly after he finished the bricks. Then he installed the windows and doors. And Rusty was much happier with this project. When this project was done, bot 1 spent a lot less time just sitting on the curb. So to achieve the same thing in our Kotlin code, we can put the code that orders the doors and the code that orders the windows in a coroutine. And we can also put the work that bot 1 is doing in another coroutine. So in other words, we're going to have each row that you see here in this diagram will be its own coroutine. And here's how the code looks like for that. We use launch to create each of the 3 coroutines. And when we do that, you see we end up with an error down here at the bottom right. And the problem is that this launch function doesn't return a value from order. So we've got this call to order, and there's an actual value that gets returned from that function, and we need that to be assigned to the windows and to the doors variables. So we're using the wrong coroutine builder here. To get a value out of it, we need to use a different coroutine builder named async. The async builder is perfect when you need to get a response, like if you're making a call to a web service and you need to wait on that resource to come in. Once you use async, you can see down here, you can call .await on that variable, and that coroutine will get suspended until that value is ready for you. So with one more small change, we can simulate this latest project of Rusty's. Instead of using thread.sleep, we can change to using a suspending function named delay. And as I mentioned before, thread.sleep is really just going to block that thread while it's waiting. So it just kind of takes a nap there, but it's not being productive at all. But delay is going to suspend the coroutine that it's in, and it'll yield that thread to be able to do other work. And then once the time's up, it'll step back in. Now, as we saw before, since we're calling a suspending function, we also have to add that suspend modifier to the beginning of this function. And now when we run this, we get the output that you see here at the bottom. And with this, we can see that the windows and doors are ordered, but bot 1's not waiting for the deliveries. He's starting on the laying bricks task while the delivery is still en route. So by using coroutines, we got bot 1 able to do more work, laying the bricks while waiting on the delivery of the products. All right, later that night, Rusty was relaxing at home, watching a race car event on television. And as the race car swooped into a pit stop, he marveled at the crew's efficiency. Within seconds, they jacked up the car, replaced the tires with precision, and filled up the gas tank. All this happened so quickly because the pit crew had multiple team members all doing different things at the same time. Rusty said to himself, if I had multiple robots in my construction crew, I bet I could speed up our project even more. So the next day, Rusty got to work creating even more robots. While building them, he considered the kinds of different tasks that are involved in his construction work. Some tasks involve hard work like moving and laying bricks, but other tasks involve only phoning for supplies and watching for delivery. So he split up his robots into 2 different teams. The first team was tasked with doing the hard work and heavy lifting, so he just called them the default team because they do the main construction work. And the second team was called the I/O team because they handle the input and output or the incoming and outgoing communications with other facilities. And each team also had a foreman who was responsible for assigning tasks to the different robots at different times, depending on what was needed at the moment. Well, when the next work order came in, Rusty was very excited to try out his new crew of robots. And here's how it went. The robots on the I/O team called the warehouses and ordered the windows and doors and watched for their arrival here. Meanwhile, the default team got started laying the bricks, and the doors were, of course, delivered first. But the default team wasn't done laying the bricks, and the bricks have to be done before we can install the doors and windows. As soon as the bricks were done, they started installing the doors because they were available and ready to go. And then, as soon as the Windows arrived, then another robot on that same team got started on installing the Windows. And this saved even more time than the previous project. So if we want to accomplish the same thing in our Kotlin code, we need to just start by understanding concepts like threads, concurrency, and parallelism. So anything that we run on our computer, whether it's our own Kotlin program or an app that you download or a service running in the background, they all run on an operating system thread. And since computers these days have, most of them have more than one processor core, we can actually run more than one thread at the exact same moment. So just like with Rusty's robots, we could use a single thread to do multiple things over a period of time. But if our computer has a multi-core processor, then we can also do multiple things at the exact same moment. So this brings up an important distinction, and that is that when a single execution path of our code bounces back and forth between two different tasks, as we said before, we call that concurrency. But when there are multiple execution paths, each running a different task at the same moment, that's what we call running in parallel. And so far, our coroutines have only run concurrently, but always on one thread. So let's get the coroutines running on multiple threads so that we can have them running in parallel. So just like each of Rusty's teams had a foreman who assigned tasks to different robots on that team, in Kotlin we've got different dispatchers, and the dispatchers can assign them to certain thread pools. So you've got a dispatcher that manages CPU-heavy work. You've got another dispatcher that tends to mainly focus on I/O work, and they have different scaling characteristics depending on the number of cores that you've got in your computer and that kind of thing. So if we want a particular dispatcher to manage a coroutine, to assign it to a particular thread pool, then we just need to pass the dispatcher as an argument to the coroutine builder like we're doing here. And again, this could be a little bit unfamiliar for people who are not working in Kotlin regularly. We've got the async is our, that's our coroutine builder. That's a function call. This dispatchers.io is the first argument to that function, and then this lambda here is the second argument to that function. So we've got the, at the top, we've got 2 going to IO dispatcher and 1 with the launch going to the default dispatcher. And now that Rusty's got so many more robots working on his construction crew, he's able to install the windows and doors in parallel. He still has to wait for the bricks to be laid first, as we mentioned. But to simulate that here, we can put each of the installation jobs into its own coroutine. So here you can see I've added 2 more launches at the bottom of the screen. That way those 2 can work in parallel as well. And now this work finishes very quickly in just about 2¼ seconds. So we've more than cut our work in half from what we started with. All right, one day Rusty and his construction crew got a call from the client, and he said, hey, Rusty, here's the thing. We're moving our entire operation to another part of town, so you know that building that you're working on for us? We just don't need it anymore, so just cancel the whole project. Well, the team was already in the middle of the job, but if the client didn't need the building anymore, it wouldn't make sense to keep working on it. So Rusty ran up to each of the robots in turn and gave them the news that the job was canceled. So they wrapped up their work and took the rest of the day off. So I mentioned earlier that we can create a coroutine from inside another coroutine, like we're doing here. And in fact, we're creating, we got run blocking, which is kind of the outermost. We've got async, 2 asyncs within there, launch within there, and then within this guy, we've got 2 more launch getting created. And so we end up with a hierarchy that looks like this at the bottom right here. Let's zoom in on that a little. You can see that better. So by structuring the coroutines into this scope like this, Kotlin is able to keep track of all of the coroutines, including their parent-child relationships, so that it can manage it if something goes wrong or if something gets canceled. That way, each one of them will be accounted for without the developer having to manually think of, like, what happens if this coroutine is canceled? Do I need to go in and cancel these other jobs? All that happens automatically for you when there's a structure around the concurrency like this. And that's why we call this feature structured concurrency. So let's see how structured concurrency applies when a job is canceled. So here we're just canceling the root level coroutine at the bottom. So we're setting up everything to start running, and then I just tell it to cancel. And Obviously, we wouldn't normally do something like this, but there are many cases in our applications where it makes sense for us to cancel work that's already started. So probably the most common scenario that you hear about this is, say you've got a mobile app and the user navigates to a particular screen, and that screen requires a download of a large document. After they're there for 2 seconds, they decide to back out of that screen. Well, we no longer need that big document to download, and we'd probably rather not have our bandwidth getting chewed up by something that we don't need anymore. And so we need to cancel the job at that point. So that's the kind of idea behind intentionally canceling the jobs that are happening. Now, whatever your reason is for canceling coroutine, when it's canceled, we, like I said, don't need to manually cancel all the children. So in our example code, we were canceling the very top coroutine, run blocking, and each child coroutine is automatically sent a signal to cancel. And so in this case, run blocking is going to cancel the 2 asyncs and the launch, and then since launch has 2 children of its own, it will reach out and cancel those as well. And all that happens thanks to structured concurrency. All right, one day, as the crew was hard at work constructing another building, client called saying, I know you've already started installing the doors, or ordering the doors, but we decided that we want a more open space feeling in the office. So I still want the building, I just don't want the doors. So this time, instead of telling all of the robots to stop working, he just went directly to the robot who was waiting on the door delivery and gave him the cancellation signal. The windows were still installed, the building was still completed successfully, just without the doors. So as we just saw, because of structured concurrency, when you cancel a coroutine, the coroutine is canceled along with its children. But the cancellation does not affect siblings or parents. So in this code, instead of canceling the whole project, we're only canceling the door job. And you can see that all the way off on the right-hand side there with the highlight. We're just kind of snuck in that cancel there. And when this code runs, the job still completes successfully, but the doors are never installed. You can see from the output down here that we do order the doors arrive, but we don't actually install them. So again, a canceled coroutine cancels its children, but not its parents and not its siblings. What's interesting, though, is that since we had the await over here, so we've got this doors waiting on this job that gets canceled, even though it's not a child of that coroutine, it still gets canceled when it calls the await, because there is a cancellation exception that ends up showing up into that coroutine when you make that call. All right, so that covers it for cancellations. Let's look at one more case, which is going to be exceptions. So Rusty and crew got back at it for one more project. And while the bricks were being laid, one of the robots on the I/O team called to request the delivery of the doors, but the warehouse gave him some surprising news. Sorry, we can't deliver those doors to you. Your client has exceeded his budget limits and can't afford any more doors. Well, without the doors and without any more money, the project just couldn't continue. So the robot canceled his work and then ran up to Rusty to let him know the situation. Well, it looks like we're going to have to abandon this project, said Rusty, who then walked over to the rest of the crew and signaled for them to stop their work. To simulate Rusty's latest project, we can throw an exception. So you can see here I'm just throwing an exception before we order the doors. Probably to be a little more faithful to the story, we could tuck that into the order function itself, of course. But here I'm just doing it before the order. And by default, anytime there's an uncaught exception inside of a coroutine, it's going to affect all of the coroutines within its scope. So here, for example, kaboom is where the exception happened. It's going to walk up to its parent, run blocking. It's going to tell him that there is an exception. That run blocking is going to cancel the other coroutines underneath it. And that includes, as we saw, anytime a coroutine gets canceled, the children also get canceled. And so that launch on the right also ends up canceling its 2 children. And so this behavior, again, is something that canceling the children, propagating the exception upward until you get to the root of the scope is something that you don't have to do as a developer. You can just let Kotlin handle that for you. Now, if you have obviously an exception that you can catch in a coroutine, then it doesn't have to blow up your entire scope. You can still manage it with catching it in the coroutine. And even if you need it to get uncaught through the coroutine, you can still configure your coroutines to be what they call supervisors, which allow them to kind of contain the blast radius of an exception so that it won't go everywhere. Well, as the sun set over the newly constructed skyline, Rusty stood admiring the work that he and his robot construction crew had accomplished. The latest building looked great and was completed in record time. He thought back a few days to when Botwin was sitting on the curb, inefficiently waiting for a delivery. They'd come a long ways. By working their tasks concurrently and in parallel, they constructed their buildings in less time, taking their client satisfaction to an all-time high. As the robots powered down, Rusty dozed off for the night, dreaming about expanding his robot crew enough to one day build a skyscraper. The end.